to discuss about this nuclear electromagnetic pulse resulting from the nuclear detonation, the protection of the data centers. So whenever that nuclear detonation takes place from a surface burst or from any mid-altitude burst or from the exo-atmospheric burst, these are the products which comes out of the nuclear detonation. The first thing what we see is the light flash. Then we see the thermal radiation where the temperature is very high. Then we see the blast. Then we see the atmospheric disturbances. Then we see the fallout. And then there is one of the most important thing which is very concerned to the electronics people is the initial nuclear radiation, where the neutrons and gammas are the major thing. And these neutrons and gammas, when they result, it results into the two type of the effects to the electronics. One is called the transient radiation effects on the electronics, what we call it the tree. And the second effect, which is the most devastating, is the electromagnetic pulse. So now that, okay, when the detonation takes place, what comes first? The first thing comes the gamma radiations. And this gamma radiation interact with the environment, and that it comes the nuclear electromagnetic pulse. Then comes the neutrons, which is in the microsecond to millisecond time. Then comes the thermal radiation, which is in the millisecond to fraction of a second. And then comes the blast or shock wave. This is the time in which the thing comes. If the burst is taking about, say, 1 megaton burst is taking, so that a field is going to fall. So at a distance of up to the 10 kilometer, at the distance of 2 kilometers from the burst, the field is as large as about 2 kilovolts per meter. And these are the very strong field per meter. And if the people, those who protect the electronic system, may be protecting the electronic system for 10 volts per meter, 20 volt per meter, and this is for the civilian one. In the case of our defense, we protect for 50 volts, 60 volts, and the 200 volt per meter field system. So that, okay, 2 kilowatt means a 2000 volt, and when the 20 volt is 100 times more than that. So this is the type of the field which will be get generated, so that there is a lot of electronics which are very susceptible to this type of the field get damaged. Exo-atmospheric burst, it is called the electromagnetic pulse. In this particular one, there is no other effects other than the electromagnetic field. And this particular field becomes a very high. It is a double exponential field. And its peak amplitude is as large as something 50,000 volts per meter. Is a 50,000 for 1 meter, and its rise time is about a few nanoseconds, about say 1.8 nanosecond. And its duration, half duration, is about say 25 nanoseconds. Now you can think that, okay, which system will respond to protect this particular system? Of course, we have got the lightning is the natural resource which gets generated, but lightning is in the microseconds. It is in the microsecond. So microsecond, there's enough time from the nanosecond to nanosecond is 1,000 times. So the devices to be protected, by the time they respond to that, the whole of this electromagnetic energy from the EMP goes to the electronics, and electronics get both functional damage or operationally upset it can happen. So the energy in this particular one, tens of megahertz, and its frequency components is as about 500 megahertz. So that anything which is in this particular band of the frequency will get coupled to that energy and will go to the electronic system. So that, okay, depending upon, because I will concentrate more on the high altitude electromagnetic pulse, because that is the most devastating effect without having any other effects or the nuclear effects. So suppose when the height of the burst is the thing that, okay, it is about the 100 meters, so that deposition region which forms is the different, is about, say, this is the distance, about, say, 400 meters. So if it is that about 200 meters, it is forms around, say, 650 meters. And that is the height of burst is 300 kilometers. It is reaching about, say, 1,000 kilometers. So that, okay, you just see that, okay, on the top of that, the deposition region will be such a large, means that, okay, it is about 1,000, 1,200 kilometers. So then it means that there are that, that EMP which gets generated by these particular pulses. We have got nowadays 3 pulses, which is the IEC specifications. And in this one, the E1 pulse is the fastest pulse, is a very short pulse. Its rise time is 0.1, 0.8 nanosecond. To the 23 is the half magnitude and half, the full width. E2 is the pulse, something similar to your lightning pulse. It is the rise time is in the microsecond to the millisecond. And that, okay, we have got the third pulse, E3 pulse, which is in the few seconds to the tens of seconds. And so, okay, most devastating effects which can call to the electronics by this particular E1 pulse. Because see, it is such a faster. E2 pulse, of course, we keep on taking the care from the lightning protection, lightning electromagnetic pulse, which is in the thing. And then the E3 is the under the effect, which is the critical infrastructure, particularly the power grids, is a very important. It is like the geomagnetic storms, and its energy is enormous energy in this particular pulse. And frequency wise, if you see, the E3 is in the hundreds of hertz, and E2 is about the megahertz, and E1 comes about in the frequency domain, it comes about the megahertz. If I have the 200 kilometer, then the detonation can cover this much. If it is a 300 kilometer, it goes about covering the all the neighboring countries also. So this is the type of the thing. In this one, no other effect is coming except that, okay, we have got the electromagnetic pulse which is coming. So that if in the case of surface bus, about say kilometers distance, all the electronics which will be there, they will all burn, right? You can see that, okay, about say 400 meters, 500 meters if they are not protected. In the case of the extra-atmospheric bus, we have got the power lines, we have got the telephones line, we have got the radar system, we have got our communication system. All will get damaged by this particular field because such a strong field of the will be there. Protection of these particular systems. So then, okay, it comes about that the almost certain failure with this type of the thing if the electronics is not protected with the type of the protection which is required for this system. How that, okay, when we are looking into the design point of view, that, okay, how do you do? First, the thing that, okay, we do the design analysis. As I told you that, okay, what are the electromagnetic characteristics of the particular system, of these weapons, whether it's a surface bus, mid-altitude bus, or extra-atmospheric bus. Once we do the know the field levels, when we do the design analysis, and once we do the design analysis, we say how much field has been put into those systems in terms of the open circuit voltage and short circuit current. And from there, then we start incorporating the protection. What the type of protection to be done, whether it's a non-linear amplitude limiting protection or the frequency limiting protection. Once the protection has been done on that particular facility, then it is to be done. EMP is to be simulated, and it is to be tested by the simulated environment and to see that, okay, whether they are complying with the requirements. Then the hardness assurance testing. And that when we do the protection, it starts from the design. You can't do that, okay, retrofit in this type of the protection. What the thing that, okay, you use component label, you do the circuit label, you do the equipment label, you do the subsystem label, and then you do the system label. So it goes from the bottom to up, right from the design stage, component selection, to the circuit design, to equipment design, subsystem design, to system design. So the different incorporation has to be done. So when we do at the component level, we make the less sensitive components. I won't go very detailed into that, but circuit levels is the terminal protection devices. We call the TPDs. TPDs are the linear and the non-linear protection devices. Then we design the circuit, which we do all in the EMI EMC design. The same thing is being done in the case of the nuclear electromagnetic pulses. Then we do the circumvention. Of course, the circumvention is not applicable to the EMP. Circumvention is the process by which you sense the event and then switch off your system so that it becomes the more hard. But in the case of the nuclear detonation, EMP is the first thing which comes to reach to the system. Then we have got the equipment, subsystem and system level. We do the zoning, electromagnetic zoning. We do the clustering of the system, layering. Then we do the different cable layout, their configuration, their impedance control, their different type of the shielding. There's a, that super screen cable, their transfer impedance is to be minimum 0.001 milliohm per meter type of the thing. Then the shielding has to be done. Shielding integrity is to be maintained by the gaskets, by the, finger shapes with the honeycomb filters. Then we have to do the grounding schemes and the different type of the thing. There, the crowfoot grounding, the fishbone grounding is there's this, that distributed ground stream. Then we have got the damping. Damping means that, okay, because the pulse which is going to get that one, so the electromagnetic energy has to be get damped by the electromagnetic absorbing materials. Now coming to the critical infrastructure of the country. It is the thing that, okay, everywhere that, okay, you see the electrical power system, telecommunication system, banking and finance, petroleum and natural gas, transportation, food, water, emergency services, space, government, and defense. These are the critical infrastructure. This whole electrical power grid of the country is being controlled by the computer. I mean the SCADA, right? Is controlled. There's nothing to do with the bigger transformer. Some solutions of this particular one, so when we are talking about the solution, this is the one of the impervious shield, if I can make. This is the idealistic case. Nothing can go inside this or nothing can come outside of it, right? But in practice, I will not have a system like this. I will not have impervious shield. I will have a system like that. In this particular building or in this particular facility, there will be the power line will be coming. There is the communication. There is the control cable. There is the antennas. There is the doors will be there. There is the windows will be there, and that is different thing from power is going from one system to other system and all this one. Now, suppose we have got the system like this, and it is this type of thing. How we protect this particular system? Then we have got the two type of the solution. One we call the system level protection. In this one, what we do that, okay, we make this particular is the electromagnetic shielded enclosure, or say topological electromagnetic shielded. Topologically, I mean that, okay, where the openings are there, where from these cables are entering, we provide the protection on this particular place. Rest of the place, it is shielded, right? So this is the system level. These are the terminal protection devices. And then that, okay, at the doors and the windows and other things, windows means that we make the waveguide below cutoff filters. So this is the type of the thing. So that in this one, again, the secondary level protection we provide at the equipment level. Still, if some field can get leak inside that one, that is provided at this equipment level or in the different places. Second one is the thing when the systems are very distributed. In the case of this, most of the systems are distributed. They are not inside a building. They are distributed from here to there. In that case, we do the distributed type of a protection. What we say that, okay, we make the volt here, so the power which is coming, we have the filters here. From there, we run the shielded cables or fiber cables, depending upon the situation. So this has been the distributed type of the protection or topology which has been done. Even that, okay, we don't treat in the case of, because every doors and every surface cannot be treated. We leave it at that one. So we identify which is the place in this room. This is my place where the computer is there, where my system is there. So then we start protecting it. I will show you that, okay, suppose this is a communication facility. This is a communication facility. I have got that, long power head lines. I have got the telephones line. I have got the underground cables which are coming to that. I have got certain antennas. And I have got the ventilation panels. I have got the, some opening ducts and other things. So in this particular one that, okay, what the way that we have to provide the protection. It means that, okay, if it is a shielded enclosure, if the shelters there, is a shielded enclosure there, then what we do that, okay, we provide from all these cables, which is going, we provide a terminal protection device for these cables. We provide the EMP filters, or EMP filters mean these are the both non-linear and linear filters. Then we provide the honeycomb filters for the ventilation. Then we provide the doors for the that with the finger strips, with the shielded EMI gaskets and other type of the. So this is the way that that.
Now, my subject is protection of modern electronics, fundamental requirements in the electrical system, because the electrical system must be stronger to support the electronic installations in case of any kind of a failure or any kind of a disaster. My subject, all of you know that EMI and EMC, it has got a source, a coupling path, and a victim. And also the intentional electromagnetic pulse, which is becoming an important subject in the future. That means even electromagnetic generators, which are mounted in vehicles, can come to smaller installations, and it can destroy electronics. These are going to be the threats of future. So what we should do is protecting electronics is the important subject, but the electrical system in the sense, starting from the transformer, your electrical distribution boards, and all those parts shall offer certain or shall satisfy certain rules and regulations. Then only the EMP protection itself is possible. So the concept which is followed for electromagnetic or EMC protection is the protection concept is called as a multi-barrier protection. This is the one recommended in IEC. See, IEC 61000 series of standards talk about the EMI EMC. So there it explains what you should do to an electronics to protect, and what you should do for an electrical system and for a building and so on. Basically, against conducted and radiated effects of various kind of EMIs, a multi-barrier protection method is recommended in the IEC standard. Now, when we come to the electrical safety standard, such as our IS 732 or IEC 60364, the same concept which is followed for protecting electronics is also adopted in the electrical safety standard, and the similar things are followed everywhere. Earthing, for example, earthing means equipotential bonding. If you make a very good equipotential bonding system, then your equipment will be very well protected. Now, with respect to the conducted and radiated surges, this is a symbolic representation. Each one is talking about, as Pandays are told, first barrier, second barrier, and the equipment. So there are barriers at various levels. Now, IEC is recommending a 6-point, 6-concept protection plan for a facility. 6-point concept or 6-part conception, protection facility means the first one, the first shielding, for example, here, the first shielding or the barrier shall protect. This is actually your building. Your building must give certain amount of electromagnetic shielding against conducted and radiated surges, for example. Now, if we have a good quality electrical building which is supporting to a modern electronic equipment, preferably the concept 3 or 4. This chart is actually from the IEC 61000. 2, 3, 4, and 5. They recommend this phenomena or this kind of a protection scenario for protection of buildings or electronic equipment in buildings, civilian facilities. So the protection concept 4 or 3 is actually possible if we design and install our electrical and electronic installation, or if we design our building in order with an aim to protect the electronics from such disasters of EMI. So with the concept 3, for example, the radiated disturbances inside the building, it still goes up to 5 kV, and these are the limits which is produced. Now, what I am trying to explain to you is, if you look at the any of the international, any of the standards with the EMI EMC, the foreign standards like American standards or British standard or whatever, what they say is the basic electrical system shall satisfy the national wiring rule. That is regarding the safety. For example, if we look at the American standards, they always say electrical system must be as per NEC or NFPA 70, both are the same. So over and above this, the other additional safety features are built. When it comes to India, we have the IS 732, which is equal to the IEC, NFPA or NEC of America. This IS 732 is from IEC 60364, talking about the design, erection, and testing of the electrical installation. There are 4 major safety measures which we are supposed to include in the installation, out of which the 4th one, voltage disturbances such as fault in high voltage. The 4th one is the subject which is talking about EMI or protection of electronics. One of the first subject here we have to discuss is the system earthing. System earthing in the sense, how are we going to earth the electrical system? Electrical system earthing is classified into TNC, TNCS, TNS, TT, IT. There are several, classifications, but preferably for a large scale area, a large scale installation where you have your own transformer, we are supposed to go for a TNS system for electrical installation and IT system for some of the critical items. But when it comes to India, the TNS is very clearly specified and written in the standard. But the question, are we following it really, is a question. Once when it comes to equipment earthing, electrical equipment earthing, there are different purposes for earthing. For example, with a different application, I always try to explain this subject in detail, but today our subject is not about earthing, so I don't want to explain it much. So one should understand the purpose of earthing and do it, like safety earthing, what to do, protective earthing, what to do, functional earthing, what to do, equipotentiality, what to do. Here, the biggest threat in our country is the misinterpretation of the standards. What we generally do is transformer neutral, 2 plates connected to 2 plates, body connected to 2 pits, and each building having multiple earth electrodes. Last week I was there in a data center, so they have about 70 earth electrodes all around the building. Few weeks back I was in another data center. They have about 145 earth electrodes all around the building. So such installations are in real danger. They cannot think of protecting from EMI, EMC, HEMP anyway, they cannot even think. But still they cannot even think of basic electrical safety, because the basic electrical safety things are also violated. Lot of buildings nowadays have this kind of earthing, clean earth, power earth, lightning protection earth, separate. This is also a big mistake. I request, please don't do it. Lot of earth electrodes, then interconnecting everything under the soil is also a wrong method. This is not the standard, or this is not technically what is recommended in the books or what is recommended in the standards and practices. Every building, the first part, if you wanted to protect any electronics, you must have the protective equipotential bonding. Of course, it is implemented for mainly for shock, protecting people from shock hazard, but it has got a role in protecting electronics as well, because now the concept of functional earthing comes into the picture, and you have to integrate protective earthing and functional earthing in a building. So if you don't have a protective earthing system in your building, of course, not even, as I said, EMI, you forget about EMI, EMC. You cannot even have basic safety. Your building will catch fire. If you have so many earth pits all around your building will catch fire. Now, the last part, whenever your electrical system is completed, we are supposed to verify the system, which includes, the inspection and testing. Similarly, an electronic system, during commissioning or after commissioning, we are supposed to comply the compliance as per the IEC 61005 standard, electronic system and information technology equipment. After installation, we are supposed to do a testing, or I'm not talking about the testing of an electrical item or a device. I'm talking about the testing of the entire system, system in the sense starting from probably an UPS and all the items which is connected on the electrical network. So this testing is also compulsory, but most of you knows this IEC 60364, 10 tests are recommended in our IS 732, but mostly we don't do it. Similar is the situation for the EMI test. Mostly we are not following. So basically what I wanted to tell you is in order to have a high reliable electronic system, high reliable in the sense, not even from the EMP point of view, but for having, an electronic system which is protected from normal situation, like a fault from high voltage line should not affect the low voltage electronic equipment. So a lot of basic safety measures are necessary. But unfortunate to say that in our electrical system, are we following those things? Is if I ask the question, most of the time it is not. We are still following an earthing system which has been discarded since 1937 or 1940s. Still we go for this, 2 for neutral, 2 for body. This concept, this concept don't exist, but we still follow it, which is the first enemy of protecting these particular things. By this, I would like to stop my presentation.